Chem quest number 12, electron configuration. So the first thing we want to do is go through the information that they give us. So it says each sublevel has a different amount of energy. So that's something that's important. So I would underline that. For example, orbitals in the 3p sublevel have more energy than orbitals in the 2p sublevel. The following is a list of the sublevels from the lowest to the highest energy. So you can either memorize this or we learn ways to help us remember. And then another way to look at the list is showing the little orbitals. So we have the 1s with one orbital, and then the 2s with one orbital, because it just has one orbital. And then the 2p has the 3 orbitals because it has 3. The 3s is 1. All the s's will have 1, so you should see that pattern. All the p's will have 3. So you should see patterns. The g's are going to have the 5. Okay, note that the d and f sublevels appear to be out of place. So we go from 3s to 3p, and then up to 4s it looks like, and then back down to 3d, 4p. So what's going on? Well, this is because they have higher energies. They have extra high energies. For example, the 3d sublevel has a higher energy than the 4s sublevel, and the 4f sublevel has a higher energy than the 6s sublevel. Okay, when electrons occupy orbitals, they try to have the lowest amount of energy possible. So I would highlight that. This is called the off-ball principle. An electron will enter a 2s orbital only after the 1s sublevel is filled up. And an electron will enter the 3d orbital only after the 4s is filled. Recall that only 2 electrons can fit in each orbital, and that is called the Pauli exclusion principle. When 2 electrons occupy the same orbital, they must spin in opposite directions, one clockwise and the other counterclockwise. Okay, so let's look at our questions. How many electrons would an atom need to have before it can begin filling the 3s sublevel? So you have to think you're going to have the 1s, 2s, 2p. So 2 electrons can go here, 2 can go here, 6 can go there. So that's a total of 10. The 11th electron would go in the 3s sublevel. So we have to fill all these up before we could go into the 3s. What is the first element that has enough electrons to have 1 in the 3s sublevel? And it says use your periodic table. So I've got a periodic table here. So we're looking at the element that has 11 electrons, because 10 wouldn't go into the 3s. So that would be my sodium right there. Sodium has 11 electrons. Okay. So let's put this back. All right, what is the first element that has enough electrons? That would be sodium, Na. How many electrons would an atom need to have before it can begin filling the 3d sublevel? So if we look at the order here, we have 1s, so that's going to have 2, 2, 6, 2, 6, 2. All right, let's see what was the question. Before it can be a 3D. So 3D would have to have 10 and 10. 20. So it would have to have 20 electrons. What is the first element that has enough electrons to go into the 3D? So which one has enough to go into the 3D? So let's look at our periodic table again. So we're looking for who has 21. So that's right there. That would be scandium, SC. So we'll put this away now. So SC, scandium. How many electrons does the element boron have? All right, so we need to pull our periodic table. So our periodic table is becoming really important at this point. We need it for a lot of things. So when we're looking for boron, it is right here, and it has 5 electrons. That 5 right there is the atomic number, and that's what tells me it has 5 electrons. So the answer is 5. All right, question number 4. Below are 2 different ways of depicting the electrons in an atom. So we have what we call an orbital diagram, and this is where we'll have the lines with the arrows representing the electrons, or we have the electron configuration. With this one, we're not using the lines, we're just putting how many electrons are in each sublevel. So 1s2 has 2 electrons, 2s2 has 2 electrons, and then 2p1 has 1 electron. So the question is, in the orbital diagram, what do the atoms stand for? So we know that. That's pretty easy. Electrons. Or I like to use my E negative sign. What do the little superscripts stand for in the electron configuration? So that question is asking, what do these little numbers stand for? And those also stand for electrons. So I'm going to put the E with a little negative. Both of the diagrams represent the same element, and then they want us to name that element. Now, how do you know who the element is? You can count the arrows. So we have 1, 2, 3, 4, 5 arrows. Or we can add up 2 plus 2 plus 1, which equals 5. So this is boron. All right, now it tells me, for each of the following electron diagrams, decide whether it is an orbital diagram or an electron configuration. And then, who is it? So here we have A, that is definitely an electron configuration. So let's just circle, or should we highlight? Let's circle it. Electron configuration. And the element is who? So in order to do this, I'm going to add up all these numbers. Now, this is always going to be 10. 6 plus 2 plus 2, that's 10. And then I've got 4 plus 2, which is 6, so that's a total of 16. Now I have to get my periodic table. Who is number 16? And it is sulfur. Okay, so we figured out who it is. Put our table back. Name the element, and we're going to put S for sulfur. All right, the next one. That is not an electron configuration because the other one was, and they do not look the same. So this is an orbital diagram. Who is it? This one's kind of easy. We just count the arrows. So we have 1, 2, 3, 4, 5, 6. And then you pull your periodic table. Who is number 6? And it would be carbon. All right, so we can put this back. Carbon. All right, the next question. C. Okay, that looks like the one we just did. So orbital diagram. And who is it? Okay, we're just going to count the arrows. 1, 2, 3, 4, 5, 6, 7. So we have 7. So it's going to be the one next to carbon. So when I look to see who is that, that's going to be nitrogen. All right. All right, indeed, the last one for this question. That is an orbital diagram. And then you count the arrows, 2, 4, 6, 7, 8. We have a total of 8. And you get your periodic table. And who is number 8? That would be oxygen. So O for oxygen. Okay, that wasn't too bad. All right, let's talk about another rule. This rule is called Hund's rule. So all these rules are good to know because we have to follow them when making electron configurations. So it says, look at the orbital diagram from question 5b. Hopefully you identified the element as carbon. The following diagram has 6 arrows just like carbon's from 5b. It is technically wrong to put arrows like this. Electrons like to spread out when going into the p orbital, so we cannot pair them up together. And we've talked about that. So look again at oxygen's orbital diagram from question 5d. The diagram is a wrong way to draw oxygen's orbital diagram. And here we've got them paired here and paired here. This is wrong. Electrons like to spread out. So let's look at the correct way. This is correct. You're going to have fill up the S with 2, fill up the next S with 2, and the 2p, we have to put one at a time in each orbital, and then we pair it up. Electrons like to spread out when going into p orbitals. They also try to spin up whenever they can. So this is one thing that's not talked about first. So it says that they do like to spin up first, according to this. And then when they pair up, they'll spin down. Okay, so that's kind of a new rule we hadn't heard before. And maybe not necessarily a rule, but what do we call it? It's just something they like to do. They would rather spin up first. All right, question number 6, Hund's rule. Hund's rule is the name of the rule that summarizes the above information section about electrons. Which of the following is the best statement of Hund's rule? So this is a rule that's important. So let's look at these two statements. Electrons prefer to pair up to occupy the same orbital whenever possible. Whenever possible, electrons will be unpaired in separate orbitals with parallel spins. It would be that one. They're going to go in separate orbitals with parallel spins until they pair up. All right, number 7. The following orbital diagram is drawn incorrectly. Redraw it correctly. Okay. So we have 1s2, that looks right. So 1s, and then we have this. And then we have 2s with 2, so that looks right. We have 2p, and that's got, it's all full. So if it's filled, that's easy. Then we have 3s. Oh, I forgot the s over there. 3s with 1 orbital, and that's filled. And then 3p, and this is where the issue is. So 3p has 2 paired together right away. Well, they're not going to be paired together right away. So the correct way to write it, and we're going to go with up arrows first. You want to separate those 3. Okay, let's look at question 8. Each of the following diagrams is incorrect. We have to draw them correctly. Okay, so just take it one at a time. So the first one, the 1s2, that is correct. 1s, and then we have 2 in that orbital. Then we have 2s, an orbital, and it's filled. Then we have 2p with 3 orbitals, and each of these are filled, so that's correct. Then we have 3s, and notice there's only 1. Oh, we can't do that. We have to fill it up. So we're going to put the next electron there, and then 3p, and it's got 3 orbitals. So we have 10, 11, 12, 13. So that's 10, 11, 12. So we just have 1 more there. So that is the correct way to write it. All right, let's look at the next one. When you first glance at this, you think, well, that looks right. But what we need to look at is the energy levels and the sublevels. So we have 1, 2, and then this is 3s. That should not be 3s. So we have 1s with 2 electrons. That's correct. Then 2s with 2 electrons. That is correct. The next energy level is 2p with 3 orbitals. And this has 3s, so that's not correct. So it's going to be 2p, and this is going to be completely filled. After 2p comes 3s. 1 orbital, and we're going to fill that one up. Then we have 3p with 3 orbitals. And we're going to fill this one like that. So we had to watch here, the energy levels were not right. There was a 3s there. It was out of order. So the 3s needed to be after the 3p. All right, the next one. Let's see, we've got 1s2, 2s2, 2p6. That's correct. 3s2, and then 3p. And our problem here is the spins. They all should be spinning the same direction. And according to what we just read, they like to spin up first. So we want to change those 2 down arrows to being up arrows. So we have 1s with 2 electrons, 2s, 2 electrons, 2p. We're going to fill this up. And then 3s and 3p with 3 orbitals. We want all the arrows spinning up. Okay, the next question, number 9, wants us to take the electron configurations and put them into orbital diagrams. So, that's not difficult at all. So I just want to draw a line to kind of separate them. So 1s2, we have 1s with 1 orbital, 2 electrons. And then 2s, 1 orbital, 2 electrons. 2p, 3 orbital, 6 electrons. And then 3s, 1 orbital, 2 electrons. And 3p has 2 electrons, so we still draw the 3 orbitals. And then this is where we need to make careful we follow the rules. Just separate the electrons and make sure they're pointing up. Okay, so B is a shorter one, which is always nice. So we start with 1s, make one orbital and fill it up. Then 2s, one orbital, and it has 2, so we fill it up. 2p, 3 orbitals, and it's filled, so it's 6 electrons. And then 3s, one orbital, and there's only 1 electron in it. All right, let's move to the next one. Oh, this is a short one, so that's nice. So 1s, one orbital, we fill it up. 2s, one orbital, we fill it up. And then 2p has 5. So I just go ahead and follow the rules. I put 1 in each, 2, 3, and then I pair them up, 4 and 5. All right, question number 10. Look at the electron configurations from question 9. Now, who is it? I guess we should have counted the electrons as we were going. So if we count the electrons, we've got 10 right here, 11, 12, 13, 14. So this is 14. Then we have 10 plus this 1, so that's 11. And then here we've got 5, 6, 7, 8, 9, so that's 9. Okay, the element from question 9a is, and the only way to know that is to get your periodic table. And we're looking for the one with 14 electrons, so that would be silicon. Okay. Put that back. So silicon. All right, so from 9b, and you're looking at the one with 11. So we pull our periodic table. Who's got 11 electrons? And that would be sodium. So for this one, it would be sodium. We're just going to put the letters. And then question 9c, who is that? Have to pull in this, and we're looking for the one with 9 electrons. So 9 electrons would be fluorine, F. All right, the next question says, write electron configurations with no arrows for the following elements. The first one is done for you. So let's go on the next page and see how we do that. Okay, the first one is phosphorus, and they've already done it for us, and it has 15 electrons. So one of your best ways to check this is when you're done, you add up all these superscripts and make sure 6 plus 2 plus 2 plus 2 plus 3 is 15. So as long as you can do that and it equals each other, then you know you probably should have the right answer. So neon is our next one, so we have to get our periodic table and see how many electrons does neon have. So neon is number 10, so it has 10 electrons. So we're going to put 10 right here. And I'm going to go ahead and look up the other ones so we don't have to keep pulling the chart back. So aluminum, if we look at aluminum, it has 13. So we'll write that down. And then sodium is our last one. Sodium has 11. So we can put our chart up here, and sodium has 11. All right, so we need to make sure we do the energy levels in the correct order. So you want to be referencing that first question with that listed in order for you if you need it, okay? So we're going to start with energy level 1, 1s, and we fill that up, 2. Then we have to go to the next one, 2s. We're going to fill that up, 2. So that's 4 electrons there. The next one, we'll just look up there, is 2p. So So that's 4. I've got 6 electrons left, so I'm just going to put them all there, and that's it. This is the electron configuration for neon. Now we have aluminum. Now aluminum has 13, so it's going to have the 10 just like neon, so we can just go ahead and write that. 1s2, 2s2, 2p6. Okay, that's 10. The next one is 3s. We're going to put 2 in there, so that's 10, 11, 12. Then we're going to have 3p and with just 1. So that's 10, 11, 12, 13. So this is the electron configuration for aluminum. The next one is sodium. So once again, just follow what you already have. You've got 1s2, 2s2, 2p6, that's 10. Then we're going to have 3s with just 1 more, so that would be 11. This is the electron configuration for sodium. All right, number 12. The following electron configurations are incorrect. Fix them. All right. So A, we've got 1s2, 2s2, 3. Oh, I see the mistake. There's 8 electrons, but there shouldn't be 3s right here. It should be 2p. Okay, so we have 8 electrons, 2, 4, 6, 8. So this is the correct way to do 8 electrons. 1s2, 2s2, and 2p4. All right, so let's look at the next one. We've got 1s2, correct. 2s2, correct. 2p5. Okay, that should be 6. We have to fill it up before we can go to the next energy level. So this would be 1s2, 2s2, 2p6, and then 3s1. So let's check. We've got 10, 11, and we've got 5, 6, 7, 8, 9, 10, 11. We've got 11 there. Okay. I can already see the mistake here. 8 in a P. That's not going to happen. And then a 4 in an S. That's not going to happen. All right, so to correct this, it's going to be 1s2, 2s2, and 2p6. Let me see how many electrons we have. 8, 9, 10, 14. So that's 10. So 3s2, 11, 12, and then 3p2, 13, 14. All right, and D. First, let's count the number of electrons. So we have 6, 7, 8, 9, 10, 11, 12. There's 12 electrons. So that kind of helps us know how to do the right one. So let's just take 12 and do it. So we have 1s2, 2s2, and 2p6. That's 10. And then we have the 3s, and it should be 2. So that's it. I didn't really have to look to see what's wrong. Just find out how many electrons are there, and then I'm just going to do it the right way. All right, number 13. Nitrogen's orbital diagram is this. Nitrogen has 3 unpaired electrons and 4 paired electrons. Define the term unpaired. So what does that mean? So basically, you have an electron that's all alone. So we'll say an electron, use abbreviations, alone in its orbital. All right, in question 14, how many unpaired electrons does oxygen have? Well, in order to do that, we're going to have to do the orbital electron configuration. So oxygen, let's pull up our periodic table. Oxygen has 8 electrons. So let's do an orbital electron configuration. So you have 1s, and we put 2 there, 2s, 2 there, 2p, we've got 3 orbitals. So we have 4, and we've got 4 more. 4, 5, 6, 7, 8. So the question is, how many unpaired electrons does oxygen have? 2.